Today I continue the topic sets, in which now we are discussing universal set. Universal set means what? First I give the definition for the universal set, then I can show you with the examples. There are some sets under consideration. They are supposed to be a set which is a superset of all the given sets. Then that is called universal set of those sets. Once again, if there are some sets under consideration, thereby happens to be a set which is a superset of all given sets, that is called universal set of those sets. Universal set is denoted by the symbol U. This is universal set. With example, you see that suppose let A is equal to 1, 2, 3, 4 and B is equal to 5, 6, 7 and C is equal to 8, 9. These are the sets. Universal set is denoted by U, and this must be 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, this is the universal set. Here you see, if there are some sets A, B, C under consideration, thereby happens to be a set which is superset of all these sets, that is U, and this is called universal set of those sets A, B, C. Now you can say how we understand here A is subset of U, even B is subset of U, and C is also subset of U. These are all subsets of the universal sets. But basically the sets under the consideration are all subsets of the universal set. So universal set is the superset, you can say. You know already superset means what? If A is a proper subset of B, then B is called the superset of A. That already we have defined. Once again, if there are some sets under consideration, thereby happens to be a set which is a superset of all given sets, then that is called universal set of those sets, and that is denoted by capital U. Now after this I want to discuss about Venn diagram. Venn diagram means what? Look this. Venn diagram, I say that. Venn diagram. Venn diagram means what? As you know, the relationship between the sets represented by Venn diagram. The relationship between the sets are represented by the diagrams. Those diagrams are called Venn diagrams, you can say. And Venn diagram consists of a rectangle. See, this is a rectangle, and closed curves like circles. Suppose U is the universal set and A is the subset of the universal set. And here you see that suppose if I say U equal to 1, 2, 3, 4 and A is equal to 2, 3, how we represent? So the elements of the subsets always written in the circle only, and rest all you can see this here, what you say 3, 4, you see that 2, 3 I have written, and here you write that remaining 1, 3, 1 3 1 4. See, 2 3 are in A, 1 2 3 are in U, and ultimately you can say that A is a subset of U. A is a subset of U, and this is a way of representing the Venn diagram. Venn diagram is the diagram which gives the relation between the sets, and Venn diagram consists of a rectangle and enclosed curves, usually the circles. The elements in the sets are always entered in the circle. So this is the way of representing the Venn diagrams. So basically you try to understand, if you go for more number of subsets, if you say, and if I go for another example, I say that here, suppose let U is equal to 1 2 3 4 5 6, like this. Suppose A is equal to 2 3 and B is equal to, you see that 2 3 4, if you see that B equal to 3. So how to represent this in the Venn diagram? And this is universal set, and A is a circle that we have given, and here you have to say this B is a subset of A. First you have to write B. This is B. This is B. Inside is what? 3, and outside is what? 2 4. Try to understand how we represent the elements which are in the set 3. That element is entered in that circle B, and 2 3 4 are in the circle A, and the rest you see 2 3 4, and you try to understand how we write the remaining are what? 2 3 4, and you see that 1 5 6. This is the case. In the universal set you see 1 2 3 4 5 6, whereas A is 2 3 4 and B is only 3. This is a way of representing the Venn diagrams, and try to understand that how we represent B is a subset of A is a subset of the universal set U. This is a way of representing the Venn diagrams. Venn diagrams, actually it's named after that logician, that is Venn, and after him the diagrams are called Venn diagrams, you can say. And now after this, what we are going to study, that basically we go for representing after Venn diagrams. There are two operations we can say. One is intersection and other one is union. So the intersection and union are the two operations on the sets, that I want to take it simultaneously. Look this, operation on sets. Operation on sets. How many operations we can see? That two operations. One is union of sets, and other one is, you can see this, that intersection of two sets. Intersection of two sets, or you can see that union of two sets. Look this, these are the two operations on sets. One is union and other one is intersection. And here we define the definition, example, properties of these operations. First we discuss with what is the union. Suppose if you see that A and B are two sets, B two sets, you see. Here also you can see that in intersection A and B are two sets, because when I take simultaneously, and you can understand that how the difference can be made while union and intersection. So here you have to see that these two sets, union of A and B, and union of A and B is denoted by A union B, right? Union of A and B is denoted by A union B, like this. It is a union symbol, or you can write symbol is like this. And A intersection B, we write like this. And try to understand how we write it, the difference. So union of A and B is a set which are the elements in A or in B, you can see that X such that X belongs to A or X belongs to B. This is the definition of union. And here if you see that X such that X belongs to A and X belongs to B. This is the definition of union and intersection. So union and intersection, you can see that the elements in the intersection must be common in both, and union means that is either in A or in both. So that is why you have to consider the this is set builder form, you can say set builder form union, set builder form in intersection. So that is why here always you understand that the definition we take it that A and B, that is the two sets, and the union of two sets A and B is and consists of all those elements of A and B and common elements being taken once. See, union means all the elements of A and all the elements of B and common elements taken being once. This is the working rule of finding A and B means what? All the elements of A and all the elements of B and common elements taken only once. But whereas in intersection and common to both, the elements must be in A and also in B, and that is called the intersection. So here when you see that diagram, that how we write it, this diagram that I want to explain here. Diagram means that already I have told you, Venn diagram. See, this is Venn diagram, I have to draw both. See this is a union, this is a universal set, and A and B, this is A and this is B. Once again I am explaining briefly that A and B are the two sets. And here you see that the same way in the case of intersection, you see that A and B are two sets, and of course this is U and this is B, and A union B is represented this shading portion. So shading is like this, shading is like this. This is A union B. Look here how we write it. This is A union B. Shading is done entirely this, and you try to understand that this is A union B. This is A union B. I hope you understood how the diagram is taken according to the Venn diagram, how we represent the union of two sets A and B. Whereas intersection is only in this part, this is shading part, and here you see this, and this is the A intersection B, and whereas and this entire is this is A union B. I hope you understood that what is intersection and what is union of two given sets. And definition already I have told you, union is also the set which consists of all the elements of A and all the elements of B, and the common elements being taken once. Whereas A intersection B and only those elements which are in A and B, that is called intersection. And these are the symbolic representation of union of two sets, intersection of two sets by Venn diagrams. But now I want to discuss that how we go for considering the properties. Operation on sets 2, union and intersection. And here I have seen the definition, and here also I have seen the definition. Now I go for properties on union and properties of intersection, and accordingly we have to go for working problems later on. So only the properties I am considering in both the cases. First I have to tell all the properties and in what? Union, and later on intersection. So why I am giving the comparison? So that you can remember what exactly makes the difference. So look here, that properties may be proved with taking examples, and accordingly you can write it. So in case of union, suppose A and B are the two sets. A union B is always equal to B union A. What is this? Commutative law. You know, this is the commutative law. Commutative law. I hope you understood that in numerical A plus B equal to B plus A, commutative law for addition, AB equal to BA, commutative law for multiplication, A union B equal to B union A, and this is you have to see that commutative law under union of two sets. Whereas same property you can consider that A intersection B is equal to B intersection A, and this is also called commutative law. Commutative law under union and intersection. I hope you understood that commutative law is always. This can be proved with examples, not any other way that you can understand. So now you have to see that how we take it to the associative law. Associative law, three sets are required. So try to understand that three you have to see B union C, and try to understand how we write. A union into bracket B union C is equal to, you have to see that A union B bracket complete union C. See, this is associative law under union of two sets, union of three sets you have to say. And here also same thing, that A intersection into bracket B intersection C is equal to A intersection B complete intersection C. And here is also, this is associative law, and this is also associative law. And you see that associative law for union of two sets, associative law union of two sets, and also intersection of two sets. And here you have to see that basically if you go for the null set, A union null set, and you have to see that only A only we find. A union of null set. Null set means the set which has no elements. Whereas here you have to see that A intersection null set. Here you see this. A intersection null set. And here what we get, this is, you can see not A, this is null set only you find. Because when no common elements, and ultimately you can see that null set. So pi represents the null set that you can see. So here you have to see that when you say that, when taking two sets, that A union A is equal to A. And here also you can see that A union A equal to A, and you tell me A intersection A is what? Here also A, because common elements, here also common elements. You see that how these properties, these laws, that is called idempotent laws in general, that you can say. And you see that union, particularly one more intersection, A union U, you can see that U is the universal. And what we find this? And here you can see that ultimately you have to see this universal set. Universal set only you have to find out. And basically that you can see that that is a law of inversion. And similarly you can see that when you go for A intersection, so ultimately you will get it A, because only the common elements we will find, These are the properties of union of two sets, properties of intersection of two sets. So thereby one can go for understanding the two operations on set. One is intersection and other one is union. And here you see that basically that examples, and accordingly Venn diagram, and that already I have told you. But now you see that common, that how we go for discussing in case of taking Venn diagrams, that is under the union of two sets. Suppose if I say the two sets are there, if I show like this Venn diagram, look this is the universal set, and there are two sets I want to take. This is one set, and this is A, and this is another set, this is B, and you try to understand this is set A and this is set B, and these are not having common elements, nothing, and such, see, this is A intersection B is null set. A intersection B is null set, no elements in common, and that is called, these are disjoint sets, we can say. These are disjoint sets. So when you say that two sets are disjoint, A intersection B is null set. The Venn diagram is like this. And here you have understood that disjoint sets means what and why they are disjoint and how to write this. And rest of all we go for discussing in next part. But here I have defined disjoint means their intersection is always what? Null set. So here one more law that I can discuss is combined together. What combined together? So that you know the distributive law that you know. Distributive law you know that in plus and multiplication. Here you can see intersection and union. Look this. This is called distributive law. A intersection of B union C, that intersection distributes over the union. So this is written A intersection B bracket complete and union A intersection C. What law this is called? Distributive law. Here that union distributes and under the union you can say. What do you call that? You know the distributive of multiplication. And likewise here you can see under union and intersection. A union into bracket B union C equal to A intersection B union A. So these are also can be represented by Venn diagram. That you can show in the textbook and thereby you can understand that how distributive law is considered. Now finally in this chapter we have to go for considering that two sets that difference of two sets we are discussing. Difference of two sets. How we are understanding this? Try to understand A and B are two sets. Here you see A and B are two sets. Then how you difference means you may go for A minus B, even you can go for B minus C. Both are correct, difference. But how you say that A minus B is a set that is X such that X belongs to A but X does not belongs to B. So this is the definition. A minus B is a set in which the elements are belonging to A, those are not belonging to B. That is called A minus. Similarly, B minus A is also the set X such that X belongs to B, but what you say, X does not belongs to A. So this is also difference of two sets. And here you are understanding that A minus B is also set, B minus A is also set. A minus B is the set in which only the elements of A are considering, and B minus A only those elements we are considering which are present in B. So this is nothing but A and B. But how we represent in Venn diagram? Look this is whenever Venn diagram you have to go for, you have to see the rectangle and two sets I am going to take. What? See this, and this is A, this is B, and you know this is U. What I say? A minus B and A minus, this is A minus B. A minus, see the A minus B is how much? Only this portion. Only this shading you understand how you are doing. A minus B. So this is A minus B. Why this is A minus B? Only the elements which are present in A but not in B. This is A minus B. Suppose if you go for B minus A, look this Venn diagram. If you go for, this is universal set, you see this is A and this is B. And you see that where B minus A? B minus A is, you have to only see this. And you see that this is B minus A. And shading you observe here. Here A minus B is how much? This is B minus A. And look here, A minus B, that shading portion, here B minus A is shading portion. But while completing this difference of two sets, and usually you have to say that in a set builder form that already I have explained. Now we go for this difference of two sets in a specific order, and thereby I want to tell the word again disjoint. So what I want to tell, A minus B and B minus A and A intersection B are mutually disjoint. See here, I want to take this very confusing this, I want to take bigger figure so that you can understand how they are mutually what? Disjoint. Suppose you say this is U. Suppose if I say this is A, look this is A, and I say that this is B, and you try to understand this is A minus B. A minus B is what? A minus B is this, you see, A minus B is this. See, I want to tell this is A minus B or not. This is A minus B. Try to understand A minus B, this is. This horizontal lines which I have shown here, you know, it is A minus B. And here you go for this. This vertical line what I have shown here, and here what is this? Here you can see that very interestingly this is B minus A. I hope you understood this. This is A minus B, this is B minus A, and try to understand this is there, you know, this, and you see that what is this? This is, you know, A intersection B. There are three sets I have shown here: A minus B, A intersection B, B minus A. These three sets are mutually disjoint. Disjoint means there is no common element. Suppose if you say A and B are disjoint, A intersection B is a null set. See, mutually means A minus B, A intersection B. Is there any common elements here? No, disjoint. Even you see that A intersection B, B minus A, no common disjoint. Or you can see any two separately you take, and that null set we will find. And hence what we can see, A minus B, A intersection B and B minus A are mutually disjoint. What you say? Mutually disjoint sets. But here when they are mutually disjoint and you try to understand A union B is what? A union B is entirely, A union B is, you have to see this all A union B, now this, and then A union B is what you are writing here, all you are writing this A union B, so you are writing that A, what you say, A minus B and also A intersection B and also B minus A. So these three sets, when you take it common, because all are mutually perpendicular, and you have to see that how they consider while writing this, and naturally you have to tell that A union B is including A minus B, B minus A, and what do you say, A intersection B. So one thing it is true that later I am explaining, A union B means what? Including all these sets, mutually disjoint sets, and accordingly we can see that if it is union, you say that A minus B plus A intersection B plus B minus A. So once again you understand, when they are disjoint, then you are writing plus there. So I hope that how these three sets are disjoint. Why I am telling? Because next some derivations we have to go for, in which this idea must be utilized. There we can understand, otherwise derivation may not be understood clearly. For that purpose I have taken here. So one thing it is true that when you go for taking the disjoint, and you have to go for writing the plus points here, and then number of elements, whatever you say. So already I told you that in case of power set, that the number of elements in the set A, that is denoted by n of A. We can write the number of elements of A, n of B, number of elements in B, n of C, number of elements in C. Suppose if you say A union B, n of A union B is equal to n of A minus B plus n of intersection B plus n of B minus A. Why? Because all these are disjoint. A union B is, this gives number of elements in A union B is equal to number of elements in A minus B, number of elements in A intersection B, number of elements in B minus A. So now we go for studying finally that complementation, and that is the end of this chapter. After that we go for some derivations, and that completes the chapter. So what is the complementation? You see, complementation. See, complement. So first you understand that what is the complement. Complement means complement of a set. You have to understand. You try to understand what is the complement of set. Suppose you say universal set is 1, 2, 3, 4, and suppose A is the set, for example 2, 3. What is the complement set of A is denoted by A to the power T or A to the power C, but here I am writing dash. This is nothing but only those elements excluding 2 and 3, that is nothing but 1, 4. I hope you have understood that the complement of set A is nothing but here we have to go for what is, see, complement of set in set builder form, X such that X belongs to U, but X does not belongs to A. Complement set of A is a set which consisting all those elements of universal set, but excluding the elements of A. That is called complementation. So X belongs to U, but X does not belongs to A. That is called a complement, you can say. So usually complementation or complement, that you can consider easily. And you see that when complement, you see that A is also subset of universal set, and A dash complement is also subset of universal set. But one thing is true, you can verify with the example, complementation of complementation. See, A complement of complement is always A. This can be proved with examples. For example, here you see that A dash, and you have to tell that what is the complementation of A dash dash. A dash complement of only excluding 1, 4. Excluding 1, 4 means what again you have to write? 2, 3 only. What you say? 2, 3. And what is this? This is nothing but A complement of complement is that set itself. So this is the way of proving complement set of the given set. Now you can see that how some important derivations we are to consider at the end of this topic. But here it is true that how we represent them in other way, that is correct. So one more important in case of complementation, that should be considered. But now union and intersection also can be seen in the complementation. So one example I am taking, and that completes your doubts if anything else are there. See example, suppose let U is equal to 1, 2, 3, 4, 5, here you see that 6, 7, 8, 9, 10. Suppose if you say let A is equal to 1, 3, 5, 7, 9. So you tell me that what is the A complementation? A complementation means excluding A you have to write. Excluding A, excluding means 1, 3, 2, 4, 5 is there, 6 and 7, 8, 9 is there, 10, yes. So this is the complementation of this. The elements which are belonging to U but not in A, and that is called the complementation, you can say. And even if you see that with the universal set in the same manner, you can consider, suppose universal set, if I take only few numbers here, 1, 2, 3, 4, 5, and accordingly you can see the result here, 1, 2, 3, 4, or else you take 6, and let A is some elements, you can say in this case, that is 2, 3, and B is you see that 3, 4, 5. Now I want to tell that A dash B dash. You know that A dash is, A dash means what? 2, 3 you have to drop. 2, 3, 1, 4, 5, 6. And what is B dash? B dash means you have to drop out the 3, 4, 5. 1, 2, 6. And here you have to understand that how to prove this A union B dash, how you are finding. A union B bracket dash, I am writing. First you have to find out A union B is what? A union B you have to find out, then only you can see that how other things can be done here. Or you can see this basically if you go for intersection, and this implies A intersection, A dash intersection B dash, means that A complement intersection B. See, is there any common elements you can see? 1 is there, 2, 3, 6 is there. So A intersection A dash intersection B dash, A complement intersection B complement means, so here. And one more thing is that, suppose if I go for A union B is what? A union B. A union B means that here A and 2, 3, and you have to see that A union B. You see that all elements not repeating, 2, 3, 4, 5. So this A union B, 2, 3 is there, and 3, 4, 5 also. So what is the complementation of A union B? You see A union B complementation. The elements which are not in U. So 2, 3, 4, 5. 2, 3, 4, 5 means you have got 1, 6. So what is this? 1, 6 is here also. That is nothing but A dash intersection B dash. So what we have proved here with this, understand here, A union B dash is equal to A dash intersection B dash. Once again, A union B dash, dash means complementation equal to, and similarly you can prove that A intersection B dash is equal to A dash union B dash. So these two are called De Morgan laws beta. And which are the two De Morgan laws? A union B bracket complete dash, A union B complement is equal to A complement intersection B complement. And also you can say A intersection B complement, A intersection B dash equal to A dash union B dash. And this is called totally De Morgan's law, you can say. So one thing it is true that if you go for writing A complement, how we represent in the Venn diagram. So once again that you can understand that I want to represent a complementation Venn diagram we represent, and this is U. Suppose you see that let U is equal to 1, 2, 3, 4, 5, and let A is equal to, you see that particularly you can write that any elements you can see that 2 and 4. So here you have to understand that how to represent and 2, 4, and see even this is A and A dash, how we have to take this in terms of complementation. And generally A complementation means you have to see that does not belongs to A, that belongs to U. So you can say directly that when you see that A complementation you have to write. So which are A is 2, 4. A complement, suppose if I take this is the A complementation, that is A dash, and 2, 3 cannot be written here. So A complementation is that only that not in 2, 4, and there you have to see that this, suppose if you say this is A and 2, 4 does not belong to this, and here you have to see that the A complementation means outside you have to consider like this. So anyhow, complementation is nothing but when you go for writing A and A dash, if it is A and you can see that outside is A dash, the elements which are belonging to A not belonging to. So this is actually A dash is complete dash, you can take it. That is A is 2, 4 you say no here, and A dash is not excluding 2, 4, the rest of all is considering as a complement. So you have to tell that when you see that A is this and A dash is what? A dash is that dash, you can consider this. Suppose this inverse of set. So try to understand once again how we take it this. Shading portion gives what? Shading portion is gives and the elements which are belonging to U but not A. Look this, A dash is X such that X belongs to U but X does not belongs to A. That is called A. And here is the A dash. Try to understand here that shading portion is gives. When you say this is A and you don't write numbers, this is A and this is A dash. A dash means the element which are not in A, and that is called A complementation. So this is the way how we understand that laws under sets, union and intersection. So finally we come to see that the derivations, that how we go for practical use of these intersection and union, that should be considered. And when you see that complementation, suppose if you say that elements belonging to that other than that set which we have defined. Now you have to tell that anything else to derive and practical results that I want to prove it. Now we see that practical observation, that we have to see that practical problems on union and intersection of two sets. So you have to see this practical problems on union and intersection. Of sets, that should be discussed. Now we have to discuss like this, what are the practical problems that on union and intersection. Now we continue the sets, the last part. Last part means here practical problems on union and intersection of sets. There are three derivations I am going to consider, and that should be observed very carefully. In which the first one, in the textbook they write directly, but here I want to derive practically how this can be done. And you understand derivation is not important, but the formula is important. The formula is important not only in the set theory, even you study the probability in first year, probability in second year, these three formulae we use. That is why I am taking much care about how we find these formulae which are based on union and intersection of sets. The first one you see, let A and B be finite sets. Try to understand. First I write what is the formula. If A intersection B is a null set, then the result is to be say that n of A union B is equal to n of A plus n of B. Look this result and how we prove directly here. See that formula number 1, n of A union B equal to n of A, n of B. This is a condition that if A intersection B is null set. If this condition is there and this formula is correct. So that the first formula is that A and B be two finite sets. If A intersection B is a null set, then n of A union B is number of elements in the set A union B, that equals to number of elements in the set A plus number of elements in the set B. So this formula I want to explain briefly how this can be done. Condition you remember once again, if both A and B are disjoint sets. A intersection B is a disjoint, you know. That is why you have to tell that how you say this case. And already that you have seen that in the previous part, when you go for proving that we know that A minus B, A intersection B and B minus A are disjoint sets. Disjoint sets. And already I have told you that disjoint means what? They are mutually disjoint, that already we have discussed. And you have to see that particularly A union B is what? The elements which are in A or in B taking common ones, that's all. And here you have to see that A intersection B, if A intersection B, you see, if A intersection B is a null set and no elements in common, that is understood. So basically if you see that when the result is there, when A and B, that is why n of A union B is equal to n of A plus n of B only. Why? Because you see that the elements which are in A union B equal to elements which are in A plus which are in B. Why? Because that no common elements. If common elements is there, that again the different case. So A union B is nothing but the elements in the set A union B are those which are in A or in B and common elements being taken once. And if the condition no common elements, and definitely we have to see that number of elements in A union B is equal to number of elements in A and number of elements in B. And the condition you have to take it grant that and the elements common in A and B, there is no common elements A and B. So this is more than enough to understand. Once again, A minus B, A intersection B, B minus A are disjoint. If A intersection B is, you can write and n of A, because you cannot see that common elements. Why no common elements? Condition is given that intersection is null set. So this is one formula. What is our first formula? You see once again, if A intersection B is a null set, n of suppose you go for previous, once again I repeat, n of A union B is equal to n of A minus B and n of n of A means only the elements which are in A plus n of A intersection B and n of B. This is the formula we have seen. But n of A means the n of A minus B is nothing but only those elements of A only we take. We are not taking B. So this formula already you have seen. N of A union B is n of A minus B, n of A intersection n of B minus C. N of A minus B is only those elements we are taking, the elements which are in A but not in B. And see, this element n of A intersection B it is 0. That condition is given. And second one is n of B is n of B minus A is nothing but n of B. So the result is n of A plus n of B. Once again you understand that the elements which are in A union B, definitely which are in A minus B, which are in A intersection B, which are in B minus, all these are disjoint. So that we write when this is 0 and n of A minus B means n of A, n of B minus A, n of B. So the formula becomes n of A union B is n of A, but condition is that n of A intersection B is null set. And what is the number of elements in the null set? 0. And no element. 0 means no elements. That is why you have to see that this formula is correct. What formula we have seen now? If A intersection B is a null set, n of A union B equal to n of A plus n of B. In second formula, you see that what is the second formula. And that is also considerable in this case. So in the second case, what we see that in general, you see this, if A and B are finite sets, if A and B are finite sets, then n of A union B is equal to n of A plus n of B minus n of A intersection B. A intersection B. So accordingly you have to see the result here. And now you try to understand how it is proved the result. Once again you see that n of A union B equal to n of A plus n of B minus n of A intersection B. But in the previous formula n of a, only these two we have written, and there you have seen that n null set, intersection of a and b is null set. How to prove this? Look this, the derivation. So as already we have understood that a union b is equal to what? That is n of a minus b plus n of a intersection b plus n of b minus a, because a minus b, a intersection b, b minus a, all those are definitely what? Disjoint sets. Now I write that this is equal to n of a minus b, and try to understand n of a minus b, the elements you are writing. How many elements you are writing? N of here, n of a minus b is nothing but n of a only, n of a intersection b, and n of b minus means n of b only. So here you understand that before writing this, you can understand how it is to be done. So once again you see that these are mutually disjoint sets, so that you can write, and accordingly you can see the results here. So one thing it is true that result I want to write in this fashion, whether you are clear or not. N a minus b, and see this n of a intersection b, and here I want to make it this tag, and n of b minus a, and here I write n of a intersection b, and addition, so that subtraction n of a intersection b. Try to understand, this is added and this is subtracted, no change, but here I want to make it a club here. So here you see that n of a is nothing but n of a, and what is this? N of a. So what we see that n of a intersection b, n of b minus a, n of a intersection. So how we see that, and accordingly we can write the result. So the result is that when you see that n of a intersection b, n means is nothing but what? We go for this is n of a only, and this is nothing but n of b only. So n of a and n of b when you write, and finally we come to see the results that n of a, and see this, I want to say this is n of a, I write this underline, and this underline n of b we write, minus n intersection of a. So you are getting confusion that how you have got this is n of a. But this I want to clarify once again, the Venn diagram which already I have shown you, that how you find this is a and this is b, already I have told you, and this is nothing but what? A minus b, and this is nothing but b minus a, and this is a intersection b, and a is what? A minus b, a intersection b. Yes, a minus b, a intersection b. So nothing but a, and here b minus a intersection b is nothing but b. So that n of a, n of b minus n of a intersection b. Once again, here n of an a intersection b is added and subtracted, and make it, this is how it is n of a. See, n of b minus a intersection, this is a, n of b minus this is n of b, and accordingly this formula is correct. So in general, n of a intersection b is equal to n of a plus n of b minus n of a intersection b. And now we come to see the final and last result, and accordingly you can see the final result, that is the third one. So here also we see that three sets we take it A, B, C, and we use the same ideas, and accordingly you can understand. What is that statement? You see that last, third. If A, B and C are finite sets, what do you say? Finite sets. Then this is somewhat lengthy, you understand this. N of A union B union C is equal to, you try to understand n of A, n of B, n of C, and you can see that and try to understand n of A intersection B, n of B intersection C, and here you see this minus, and minus n of C intersection A, and plus n of, you have to tell that result is A intersection B intersection C. This is the result. So how to prove this? That is a very interesting part here. Once again, n of A union B union C is equal to n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of C intersection B plus n of A intersection B intersection C, and that is the formula you have seen. So how to prove this, that I want to discuss here, and accordingly you can continue with this. So see the derivation, proof, and keep it the two results which we have derived, and that can be used here. Once again, n of A union B union C is equal to how many results? See, 1, 2, 3, 4, 5, 6, 7 additional terms that we can see. But how we find that we are explaining. First, I have to tell. See this. We know that already this part we have studied. You know what we have studied? N of A union B. What is the formula? N of A union B formula. What we have proved in general. I am talking. N of A plus N of B minus N of A intersection B. What is this? N of A plus n of B minus n of A intersection B. This is the formula that we have proved in the first result. That I have written, and accordingly you have to see the result. So how you have got this? This is the result number 1. What result? Result number 2, that is when A intersection B is not null set. Look here. Now we are interested to see that n of A union B union C. This is to be discussed, not only the 2. Here we have to discuss with the 3 elements, and accordingly we have to see that. Look this, n of first, n of second, n of intersection. This is first I want to take, this is the second I want to take. Look, this is the first, and this is, how you say, this is the first and this is second. N of first, n of second minus n of, see here, n of A intersection C. A intersection C. Look here, that n of A, first one, this first one is what? N of A, and plus n of second is in what? N of B union C. Yes, B union C minus n of that intersection of A and intersection of that is B and C, so that B intersection C. I hope you understood this. How you have got n of A first, n of B, then A intersection of this and A intersection of this and this intersection here. To see that here also you have written intersection of this. This is how much? A intersection of, here you see, what you see, n of this is B and union. See, this is second, first, second, their intersection, and this is the case. Accordingly, this I have written. How you say n of A union B is n of A plus n of E, n of their intersection. Likewise, if I go for this is 1 and this is 1, n of A, n of B union C, n of A intersection B union n of this A intersection of B union C. This is the result that you can write it, and I hope you can see this result easily. And now you see that this is equation number 1. This is equation number 1. I hope you have understood this, how you have got. How you know this? Here A is first term, B is second term. First, second, intersection of first and second. Here also A is first and is second. N is intersection of first and second. This is the first and this is the second. So now what I do here, the thing is we have to simplify this, and that simplified form, and we can write it here. So what is the simplified form, that we'll see here now. Basically, when you see that n of A, n of B, like that, and accordingly you can see the result. So you, instead of writing this one, you can go for using one more step, that finally you will understand. What is n of A? N of A. What is n of B union C? This is n of B plus n of C and minus n of what you say, B intersection C. Look this, n of A is right. This n of A union n of B, n of C minus n of B intersection C, and this is minus n of A intersection B union C. And you call this one, it is easy to tell now. So what we have explained, n of A is n of A, n of B union C is n of B minus A plus n of C, n of B intersection C, and n of this. Now what we do here, the thing is, we want to keep it as it is, we want to simplify only for this, and this simplified form later on we substitute here and try to understand that n of A intersection B union C, and that how you find it. So I want to explain this. Look, this is the formula. You have got n of A union B union C, and now I want to remove all this, and finally we have to substitute in the equation number 1. What is that equation number 1, in which we want to see that last part? Which part? I want to simplify only. Which part I am simplifying here? Only this part. And I want to take it that A intersection B union C, it is nothing but the distributive law I told. And according to the distributive law, you can say this. What is the distributive law? This is distributive law, A intersection of B union C. So what is the distributive law you have seen? This is A intersection B. What is the distributive law? A union, what do you say? A intersection C. This is the distributive law. I hope by distributive law we write like this. And suppose if you write, this implies the number of elements here you can see, and what n intersection B union C is equal to. See, the same result is there, n intersection B union C. Whatever the result we will find, and you have to take it there. So A intersection C, n of, and try to understand how you have taken n of what you say A intersection B union, and you see that A intersection C. That is the number of elements in that set, you can say. Now you see that union formula. What is the union formula? That you know, you have already understood what n of first union second, if you say, what is n of first and plus n of second and minus n of first intersection second. It is nothing but what I have told, n of A union B. Union B is equal to n of A plus n of B minus n of A intersection B. This is a formula. Same formula we apply here. This is A1 and this is 2. Yes, according to the formula, this is first and second. What is the first? N of A intersection B plus n of A intersection C. Yes, correct or not? And minus n of and union A intersection of B intersection A intersection of C. Yes. And this is, you try to understand, n of A intersection B, n of A intersection C, and minus n of A intersection B intersection C. It is all together. And now you have to tell the result, that this result and this result you have to substitute here. And from 1, what is 1? You look this, we get final result. What is 1? N of A union B union C is equal to, what is the formula? N of A, N of B, n of C minus and n of what do you say, B intersection C. This is n of A, n of B, n of C minus n of B intersection. So minus this result is above n of A intersection B union C. The result is how much? Here is there, minus, keep it inside. You see that n of A intersection B and plus n of A intersection C and minus n of A intersection B intersection C. So the final result is, look, n of A, n of B, n of C minus n of B intersection C minus n of A intersection B minus n of A intersection C minus plus n of A intersection B intersection C. And so this is the final result, but you can write in a systematic order, and that is the final. What is the systematic order? You look here to remember. What is this? You see that order is what? You see this? N of A, n of B, n of C minus n of A minus B. First I write n of A intersection B, next minus n of B intersection C minus n of A intersection C plus and n of A intersection B intersection C, or even write like this also, it is right. So this is the final result. So make it clear that n of A union B union C is equal to. So the final result is this. What? N of A union B union C equal to n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of A intersection C or C intersection A, for convenience sake C intersection A plus n of A intersection B intersection. So this is the result. So three results that we have written, and these three results we are using even in probability first year and second year. Thank you. And next class we will see the problems.